Okay, for our next example, let's think about this for a second. What if we are given the magnitude of our vector? So that's going to be the actual length from the origin to that terminal point. Um, and we're given the direction angle. Okay. Well, obviously we can go ahead and drop a perpendicular. And if necessary, we'd be looking at obviously another right triangle. So we do have our SOHCAHTOA and Pythagorean theorem back into play. So kind of the questions we want to look at, if we know the direction angle and the magnitude of the vector, how can we get back to that position vector? So basically it's the same as what we've done before in the past. Before we put these on the coordinate plane, how do we find the horizontal and vertical components? And we can do that with just setting up a few trig ratios. So that's what we're going to take a look at here next. Let's take a peek at the formulas. To find the horizontal and vertical components of the vector, again, that's going to be your A and B. Okay, remember our position vectors. Use the little pointy brackets, A comma B, where A is the horizontal component and B is the vertical component, or the X and Y to your terminal point. So the horizontal and vertical components respectively of a vector U having magnitude U and direction angle theta are given by A equals the magnitude of U times the cosine theta, and B equals the magnitude of U times the sine of theta. So again, you could easily set those up. I don't think those are anything you need to memorize. Just set up a trig function with the corresponding sides and the hypotenuse, which is going to be known, and go ahead and then solve back for A, because we know theta and we know the magnitude. Let's try an example here. All right, so we got to find the horizontal and vertical components, write this vector as a position vector would be another way of asking this question. So let's see if we can't set something up here. I'm going to start, I'm just going to do a quick sketch. It's 45-degree angle, so we know that's positive 45 degrees, which is in quadrant 1. So we'll go ahead and set up a quick little diagram here. 45 degrees, here's our vector. We'll say, split the 90 there, so 45 degrees would be about right there. We'll call that, I kind of drew that of arbitrary distance, but we're going to label that so that the magnitude or the length here of this vector v is 20. And then again, given that direction angle, we also know that this is 45 degrees. All right, so what we want to be able to do then is, from that position vector that we just kind of arbitrarily drew, find the horizontal and vertical components. So this side here is A, which is actually just the x coordinate. This would be our B for our position vector A comma B. All right, so here we go. Again, I don't ever remember the actual formulas themselves, but knowing the hypotenuse, this would be opposite of our 45. This would be adjacent of our 45. If we wanted to solve for A, we could easily set up what trig function deals with adjacent and hypotenuse. That's going to be our cosine function. So we could set this up, cosine of theta equals the adjacent side, which we're calling A here, divided by the hypotenuse, which is 20. And I kind of filled in part of that as we went here, but we'll fill in the rest of it now. Cosine 45 is again A over 20. Solve that for A. We'll just have to multiply both sides by 20 times by 20 times by 20. The 20s will cancel out over here, and we'll have A is now equal to 20 times the cosine of 45 degrees. That we can then plug into our calculator. Check your mode. What's going on here? Calculator is not functioning properly. Time up. Okay, here we go. We got 20 times. Oop, I got to switch my mode here. Make sure we're in degrees. And now we can go ahead and type that in. 20 times the cosine of 45 should give us the component or the horizontal component then of our position vector that represents a magnitude of 20 at a 45-degree incline or 45-degree direction angle. So we'll just round that off to 2 decimal places. So right now our position vector is starting to take shape here, 14.14. If we just round it off to 2, okay, now we got to go ahead and find B. Very similarly, If we wanted to find B here, we're going to go ahead and write this time. We want to know the opposite side. We know the hypotenuse, again, trying to work with the given information as much as we can. That's going to be a sine function. Sine theta equals opposite over hypotenuse. Okay, plug in our values, and we should be able to solve that out pretty quickly. So sine of 45 degrees is equal to B over 20. Multiply both sides by 20. We'll see here then we'll get 20 times the sine of 45 equals our B. There's the formula we looked at on the previous page. Let me make a little room here. And if we type that in then, we'll get 20 times sine 45 and hit enter. And there we go, 14.14. Again, that does make sense to us. This is a 45-degree angle, which means A and B should be the same. So I guess we got to recall some of those properties too. We do have the 45, 45, 90 right triangles that we could probably use to go ahead and solve that. We could have saved ourselves a step just knowing that that is a 45, 45, 90 triangle. All right, hopefully that helps. Again, we just found the horizontal and vertical components of a given vector with a certain direction angle. Also, we wrote that as a position vector, 14.14 comma 14.14.